The decisive role of hormones, melatonin hormones, can be thought of as biocatalysts. They are more or less complex molecules that are released into the bloodstream at a certain rate by the so-called endocrine glands. These glands are distributed throughout the body and act in concert to ensure hormonal balance. Some of these glands include the pituitary gland, the hypothalamus, the adrenal glands, and the pancreas. Once these hormones are released into the blood plasma, they reach all the cells in the body. But they only have an impact on those cells that have structures in their membrane capable of capturing them, called receptors. These cells that have specific receptors for a particular hormone, they are called target cells. The hormone fits into the receptor like a puzzle due to its chemical structure. From this moment on, it triggers a reaction in the cell that significantly alters its behavior. For example, it can accelerate metabolism by absorbing more sugars or stimulate protein synthesis. Melatonin. Melatonin or unacetyl 5-methoxytryptamine is an indolamine manufactured by the pineal gland. Melatonin is not just a hormone, but a fundamental player in cellular function. It appears very early in evolution, and its concentration, especially in mitochondria, is thousands of times higher than in plasma. As a hormone, it is released during the first hours of darkness, causing drowsiness and preparing the nervous system for rest. Its function is to establish the so-called circadian rhythms, that is the cyclicity between day and night, regulating sleep and wake cycles, and with them, a multitude of processes that repeat with circadian frequency in the body, thus regulating other equally important hormones. For this reason, it is considered a master hormone. Furthermore, it is fine and fat-soluble enough to cross the blood-brain barrier, acting as a neurohormone. Its name is derived from melanin, as it was initially observed that high concentrations of it could lighten the skin of toads. However, this effect has not been reproduced in higher-ranking animals. Melatonin is produced autonomously by all cells in the body. Its high antioxidant activity is believed to provide protection against chemical damage caused by glycolysis and lipolysis. Indeed, metabolic activity involves the appearance of molecules with unpaired electron pairs, called free radicals, which must be neutralized by antioxidants to prevent significant cellular damage. Impact on aging. There is some controversy regarding whether the pineal gland's production and consequently plasma melatonin concentration decreases with age. We know that newborns lack melatonin cycles, which is why sleep at these stages becomes so chaotic, with no clear distinction between day and night. However, from the 12th weeks onwards, a clear pattern is established that becomes more evident at around 6 months old. From 1 year of age onwards, plasma concentration begins to decline, with a sharp drop at the beginning of the second decade of life that marks the beginning of adolescence, inally stabilizing during the early adulthood. There is controversy about what happens next. Some studies conclude that melatonin levels decrease with advancing age, and it is theorized that this decline is the root cause of decreased sleep quality in the elderly, or at least one of the causes. Furthermore, the low concentration in blood would not affect the intracellular concentration, and therefore its antioxidant potential. Other studies, however, cast doubt on this claim. While they establish that melatonin is decreased in diseases related to aging, such as Alzheimer's disease or type 2 diabetes, others showcase that melatonin levels remain constant in healthy individuals, with a significant decrease only being observed at a very advanced age. Furthermore, it is necessary to take into account that while disruption of circadian rhythms can significantly impact the functioning of various organs, antioxidant activity occurs within each cell, where it not only neutralizes free radicals, but also stimulates the production of endogenous antioxidants. such as catalase, glutathione, and superoxide dismutase. Clinical uses of melatonin. Melatonin has been the subject of numerous clinical trials. Its widespread availability and low price have led to an explosion of studies on its role in various processes and diseases. Furthermore, its pharmacokinetics allow oral administration, making it easy to use. Insomnia, since nocturnal melatonin production coincides with the onset of sleepiness. Its clinical use has been proposed for primary insomnia, the treatment of jet lag, or age-related insomnia, with mixed results. For this purpose, melatonin can be administered in various concentrations. Liquid or in tablets are available, which may be immediate release or extended release. Their elimination half-life is 2.5 hours, so with immediate release administration, there is an early peak and then a sharp decline, while extended release tablets mimic the somatic release pattern. Melatonin has gained widespread popularity as a sleep aid, although it doesn't act as such. While sleep aids, such as benzodiazepines, are GABA receptor agonists, melatonin acts on the MALT1 and MALT2 receptors in the suprachiasmatic nucleus, thus acting as a neurohormone. Cognitive impairment and degenerative diseases. Melatonin has been proposed as a therapeutic target to improve the quality of life of patients with Alzheimer's disease, as well as a nootropic treatment based on its brain protective activity. To date, there is no consensus on the role of melatonin in the progression of the disease. And melatonin treatment is not usually prescribed as part of a drug regimen to slow down cognitive decline. Despite this, melatonin has been shown to improve some abilities in elderly patients with mild cognitive impairment. And it also presents a lower conversion rate to Alzheimer's disease during the period of melatonin treatment. However, the study did not find significant improvements neither in healthy adult nor in those with ongoing disease. The limited duration of the study may prevent long-term melatonin assessment. Some studies have pointed to particularly low physiological levels of melatonin in individuals with Alzheimer's disease. However, sleep quality in people with dementia is often severely impaired, with sundowning episodes. Melatonin may be useful as an adjunctive treatment to regulate the circadian rhythm in these individuals. Aging. As previously mentioned, melatonin antioxidant capacity and its role as a neurohormone hold enormous potential for delaying aging in healthy individuals. Due to the length of human lifespan, it is not possible to conduct a controlled, double-blind experiment. Perhaps in a few decades, we will be able to understand and compare the different variables and markers in people who report having consumed melatonin for long periods with those of the rest of the population. Regarding animal studies, the results are mixed. In some experiments with mice, melatonin treatment has led to an increase in life expectancy of up to 20%. Cancer. The relationship between melatonin and cancer is equally complex. Studies in rodents indicate that melatonin increases the incidence of cancer in treated females. However, melatonin has demonstrated anti-apoptotic, anti-angiogenic, and antimetastatic properties, suggesting increased survival in cancer patients. Furthermore, melatonin enhances the effects of chemotherapy and radiotherapy, while soothing the side effects and toxicity of these treatments on healthy somatic cells. Furthermore, melatonin treatment helps mitigate the increased incidence of cancer in shift workers, establishing a clear link between disrupted sleep cycles and cancer risk.